Hey, Math 098, we are going to move on to Chapter 6, Section 1, and it's all about rational functions. And a rational function uses this phrase ratio right here. So it helps you understand, and I think all of you are familiar that ratios are just fractions, some number over another. Now, the main thing with rational functions that we need to pay attention to is the fact that we can never divide by zero. Some number, I'll just put a c here, some constant, that's why we typically use a c, divided by zero is undefined. Which is why as we move into the first example, exercise, it's talking about the domain of the problem. Well, the domain needs to be written in such a way that the denominator can never equal zero. Because then it's undefined, and the whole premise of the domain is values that work, values for x that make the equation give you a numerical value. So in letter A, if you notice, the denominator can never equal zero because -6 is a constant. There's no x here. So there's a lot of different ways you can write this. Some people just write out the words all reals, but I think sometimes when students write that, they lose the meaning of it. So what I like to do though is let students know that we're finding values for x and saying that x is an element of the real numbers. You may remember earlier in the year where we talked about the symbol for real numbers is this capital R, this double barred R. This is fine, just writing it like this. You may see in the book, though, that they write it values for x such that x is a real number. But I've noticed that students get lost when they write that. Or in interval notation, you would just say x could be anything. Well, that goes from -infinity to +infinity. So any one of these three options is correct. So let me just change colors and talk about the next one. Because in letter B, the denominator cannot equal zero, just like what I wrote over here. But this time we can find a value for x that is impossible. And you solve this problem just like you would any other problem. Again, you're only looking at the denominator where you subtract 3 over. So x cannot equal 0 minus 3 is -3. So some students will write your answer like this. Some people might write it like values for x such that x cannot equal -3 and x is an element of real numbers. I don't care if you want to write the problem like this. If you are a student that checks with the back of the book, you might see the problem written like this. Or in interval notation would say all values from -infinity to -3 or -3 to infinity. So it's a fancy way of saying the same thing as what's up here. So pick one, and I am happy with that answer. And while I'm at it, I do recognize that students still don't, they really get confused. So let me reiterate, I don't care about the numerator in a domain problem. All I care about is that we can never divide by zero because dividing by zero is undefined. So that's why I've completely ignored the numerator, and all I need to do is establish that the denominator cannot equal zero, which is why we do this lesson after we do the polynomials, because you have to realize that we are factoring. So as I look at this one, all the factors of 6, well, the 2 that add to be 5 would be 2 and 3, except I want a -5, so let's change the sign on both of those. So we're looking at x minus 2, x minus 3 cannot equal 0. Again, completely ignore the numerator. So that tells me that x cannot equal +2. Remember, if this is a factor, the solution's the opposite. So +2 and +3. So a lot of students will just write it like that. If you want to practice interval notation, there's a lot to write. And you do have to go in order from least to greatest. I bet you guys are looking at that and saying, man, I really don't want to write it in interval notation. Well, that's fine. You can write it the way I write it here as well. So the next one the difference is we are going to find the domain and then we're going to confirm it with a graph. So using a graphing calculator, and I'll just pull up Desmos like I typically do because all of you have access to Desmos. So in this first one, well, we've kind of did a problem like this. If you set the denominator equal to 0, then x cannot equal -3. Now this one over here is a little bit more complicated because what you'd have to do is multiply. 3 times 5 is 15. Factors of 15 that add to be 8 would be 3 and 5. Make them both negative. And then I'm guessing most people need to actually write it out. -3x minus 5x plus 5. Group. So you'd have a greatest common factor of 3x, x minus 1. I'd factor out a -5 to give me x minus 1 as well there. So looking at x minus 1, 3x minus 5. And all of that work to get that x cannot equal 1, or if you add 5 over and divide by 3, 5/3, or 1.6 repeating. So as I mentioned this, I'm going to go to a graphing calculator. So I'm going to pull up Desmos. All right, so I'm just pulling up the g of x because that's the most recent one that we did. And I'm also going to write in the answers that we got. X equals 1 and x equals 5/3. And what you should notice is that I have two vertical lines. I have a blue one at 1 and this one at 5/3, 1.6 repeating. So let me just zoom out real quick and just show you that on either side the graph is getting closer and closer to those blue and green lines, but as I scroll up and up, they never actually hit those values. And same thing if I went down. Zoom a lot out, I guess. You can actually see there's a little piece of the graph below the x-axis between those two. Those are called vertical asymptotes. Vertical asymptotes are these vertical lines. Now, we don't always have vertical asymptotes when we set the denominator equal to 0, but sometimes we do. So that's exactly what's happening on this problem. Now, if you wanted to point it out, if you set the numerator equal to 0, that's actually a key point to where finding x-intercepts. Because if the numerator equals 0, that means that the y value would equal 0. So a little bit of extra information. So I'll let you investigate f of x on your own, this little piece, and you'll notice that you have a vertical asymptote at x equals -3. So as we move forward, we're going to be simplifying rational expressions. And the whole premise of simplification is that you can only, let me write this down, only cancel out with multiplication. And every year, I have students get this confused. So think of some easy numbers. So an easy number to work with, I don't know, would be like 3 and 4. So like 3 times 4 over 4 times 5. And the reason why I'm bringing these to your attention is because a person that's really quick with math would simplify this by canceling out the 4's, because you have the same thing on top and bottom with multiplication, and this equals, right off to the side, 3/5. Now, a lot of other people, though, will have to do the math in their head, like 3 times 4 is 12, 4 times 5 is 20, and then they'll have to do a little bit of side, divide both top and bottom by 4 to get the correct final answer. Now, this shortcut works with multiplication, because if I were to change that problem real quick to be 3 plus 4 over 4 plus 5, I see a lot of students try to cancel that out. The 4's will cancel, and they'll say the answer is 3/5. That is wrong, because if you actually did 3 plus 4 first, you get 7, and 4 plus 5 next, you get 9. Well, 7 over 9 can't be divided by the same number, so that that trick with canceling does not work with addition. And I see it every year, and I just need you guys to I guess pay attention for that. So my clue for you is two-factor. That way you can get the problem into multiplication. Because right now I guess there is multiplication, but it's not factored out. So in the numerator, well, there's really nothing to factor out, but I'm going to remind you that it's 5x to the fourth times 1. So that'll come into play. But if you look at the greatest common factor in the denominator, so the first thing I like to look for is greatest common factor, is both the 10 and the 5 are divisible by 5. And the greatest common factor is x to the fourth. So then you're left with 2x minus 1. And so now I have a giant multiplication problem where I can cancel out the 5, and I can cancel out this x to the fourth, and the correct answer, and that's why I wrote that 1 there, because I have other students that will cancel out the 5 and the x to the fourth, then they'll write 0 down. That's not true. It's times 1. You need a placeholder there, over 2x minus 1. And you can verify that this answer is correct by using Desmos again. So let me go back to Desmos and clear this stuff out. Let's see, it was 5x to the fourth over 10x to the fifth minus 5. So right now it just looks like this graph, and you can zoom in if you want. You can play around with it. But let me give you a new graph, which is equal to 1 over 2x minus 1. And let me move I think I can move this thing over a little bit. There we go. And I'm just going to unhighlight and re-highlight. My black curve is falling everywhere directly on top of my red curve. And I can zoom out and still see that. So that's a way that you can double check that you simplified correctly, is by playing around with Desmos. Whoops. Well, I meant to move this back, but I ended up switching screens. There we go. So let me practice letter B real quick. And I think I'm going to run out of time. I'm going to run out of my 15 minutes here. But the key is to factor. And the better you are at factoring, the quicker these problems will go. For instance, in the numerator there, I'm really good at guessing and checking, by the way. Like I'm looking at this and saying, oh, I need to get 13 somehow, but also multiply by 6. So I would think about, well, if I did 5 times 2, that would put me at 10, and then 3. So I'd have 10x plus 3x is 13x. Okay, that gave me that. And 3 times 2 gives me 6. So that's good. And then in the same manner, if this is really going to factor, what's probably going to happen is I'm going to have another x plus 2 to cancel out there. And so I could use some logic to figure out that this would be 6x. Let's see, 2 times 5 would give me 10. I'd make that a negative. And let's see if this is true. 6x times x is 6x squared. I would have 12x minus 5x is 7x, and negative 5 times 2 is negative 10. So with a lot of practice, you'll get really good at this. Otherwise, when you're first beginning, you might need to work through everything diligently and then go on from there. So the whole point of it is once you identify your multiplication, if you have the same exact binomial on top and bottom, I know over here was the same exact monomial, but we have the same exact binomial with multiplication, we can cancel them. And I'm running out of time, so I'm just going to put a box around this. I'm telling you that this answer is equal to this. One more thing before I move on is some math books will also ask you to write the domain. For instance, over here, some math books would ask you to write that x cannot equal 0 or 1/2 from exercise 1 and 2 that we did earlier. I believe our book does not, but I did want to mention that. So if you forget to do this, you'll be fine. But this is good practice before you go to college. So I'm out of time. I'll see you in the next video.